This is cm2900 sample paper question 11 part 2. We've defined the inverse transform of this expression, and we should turn this into its partial fractions. So look at the denominator. We've got a linear term s plus 1 that gets one partial fraction, a upon s plus 1. And then this quadratic here that cannot be factorised, it gets a numerator bs plus c. Then we proceed by multiplying both sides by the left hand denominator, and the left hand side, if it's multiplied by its denominator, simply leaves the numerator s squared plus 3s plus 3, and then the right hand side will be the first term a upon s plus 1 times the left hand denominator, which is s plus 1, into s squared plus 2s plus 2, and obviously the s plus 1's cancel, plus bs plus c times s plus 1 into s squared plus 2s plus 2. Now bs plus c is over s squared plus 2s plus 2, and that will cancel with the same factor from the left hand denominator. So to simplify this slightly, we have s squared plus 3s plus 3 is equal to a into s squared plus 2s plus 2 plus bs plus c into s plus 1. So if we want to find a, if we put s equal to minus 1, then this factor, this here, this bracket will become 0, and 0 times anything is 0, so that will leave us with an equation involving a as the unknown. So put s equal to minus 1, and the left hand side becomes minus 1 squared, which is 1, plus 3 is 4, plus 3 times minus 1 is minus 3, so 4 minus 3 is 1 for the left hand side, equals, here we've got minus 1 squared is 1, plus 2 is 3, minus 2 is 1, so 1 equals a, so straight away we have a. Now to find b and c, we can't really pick a value of s that will make one of the other unknowns disappear, so we should compare powers of s. So if we look at s squared terms, on the left hand side we have 1s squared, and on the right hand side we have as squared plus bs squared, and we know already that a is 1, so that equals 1 plus b. Now if 1 equals 1 plus b, b must be 0. Then to find c, we could pick constant terms. So 3 is our constant on the left hand side, must be equal to the sum of the constants on the right hand side, and we have a times 2, well a is 1, so it's a times 2 must be 1 times 2, which is 2, and here we have c times 1, which is a c, so 3 equals 2 plus c, then c must be equal to 1. So our transfer function is equal to 1 upon s plus 1, it's replacing a with 1, and replace c with 1, we get 1 over, and b of course is 0, we get 1 over s squared plus 2s plus 2, which I'm going to write as s plus 1 squared plus 1 squared. move this over a bit to make some space. Now, we know that well, s plus 1 squared is s squared plus 2s plus 1. 1 squared is 1, and therefore this denominator is the same as this denominator here. So if we're completing the square, we always divide this coefficient of s by 1, by 2. 2 divided by 2 is 1, and that gives us the term to put in here in the bracket. Now, if we know then that x bar can be written as 1 upon s plus 1 plus 1 over s plus 1 squared plus 1, then from inverse Laplace tables we can say that x of t, which is the inverse transform of x bar, is going to be given by well, inverse transform of 1 over s plus 1 is e to the minus t, and the inverse transform of this term here is e to minus t sine t. See if we can find a table of transforms just to confirm that. So this here confirms that the inverse transform of 1 upon s plus alpha is e to the minus alpha t, and the inverse transform of omega upon s plus alpha squared plus omega squared is e to the minus alpha t sine omega t. So we go back to here, we can see that how those fit with those two, that the inverse transform of 1 upon s plus alpha or s plus a is e to the minus at, and inverse transform of omega upon s plus a squared plus omega squared is e to the minus at sine omega t.